The average adult human takes just over 5,000 steps each day and is additionally recommended to be participating in over 2.5 hours of strenuous activity each week. With each step, 200 muscles in the human body are stressed and relaxed repeatedly, powering a web of bones throughout the body. One of the most critical systems that contribute to the body's walking function is the set of bones and joints called the pelvic girdle, which consists of the hip bone, pelvic bone, and femur. This means that injuries to the pelvic girdle region can be particularly detrimental. According to Medical News Today, the most common hip issues are hip fracture and dislocation, or accidents resulting from a fall or overuse of the hip. These injuries can result in a total hip replacement for some individuals. The hip replacement is one of the most successful surgical procedures, with more than 85,000 per year across the world and a 78% survival rate after 5 years. But what considerations are necessary for such an effective implant? We'll look into this and more in Precision in Motion, Hip Replacement, Engineering and Design.
In order to understand how to design a hip replacement, we need to look into how the hip functions in the body. The hip's main functions are to support the load of body weight, generate large amounts of force, and provide for locomotion of the body. In order to support the load of your body, the hip joint acts as a lever, balancing your body weight from either side of the torso with the necessary torque. Because the body weight acts further from the center of the lever than the hip does, the force needed from the abductor muscles is much greater to offset it. Just while standing, the hips must provide a force equal to 4 times your body weight, while running, jumping, and lifting requires a force 10 times your body weight. Not only do the hips need to provide large amounts of force, but the hips need to be able to rotate and provide mobility to the legs. You can think of this as a joystick. Too much friction between the joint and socket will hinder the stick movement and rotation, which would not be beneficial when trying to move, but not enough may cause the hip to fall out of the socket. This means the hip must sit perfectly in the socket to provide ample rotation of the legs, without high stresses that can cause it to deteriorate and dislocate over time. A hip implant is intended to reduce the body weight lever arm and increase the muscle lever arm, without sacrificing rotational mobility. Having a solid understanding of the biomechanics of the hip is paramount to designing and implementing a successful implant.
The total hip replacement is accomplished using 4 parts. First, the femoral stem, which fits down into the center of the femur. Second, the femoral head, which is an artificial ball that fits into the hip socket. Third, the acetabular component, which replaces the damaged cartilage in the hip socket, formerly known as the acetabulum. And fourth, the liner, which fits between the acetabular component and the femoral head, allowing for free rotation of the femoral section within the hip socket. Femoral stem begins life as a rod stock, which is cut to length. A lubricant coating is then applied. Next, the bar is heated and forged using an impression die. It is then annealed, and the flash is removed. The part is then machined, first on the mill, and then on the lathe. Next is the acetabular cup. The acetabular cup also begins as a rod stock, which is open die forged and barreled into a circular shape. Next, it is impression die forged. During the machining process, both the inner and the outer surface of the acetabular cup is turned down on the lathe. On the other hand, the acetabular liner is primarily shaped using lathing machining processes. The main considerations when choosing a material for a hip implant is design for biocompatibility, mobility, and manufacturing. In terms of the materials used, 4 major combinations dominate the market for bearings and hip replacements. Those are metal on metal, metal on polyethylene, ceramic on ceramic, and ceramic on polyethylene. The metal on metal bearing has benefits of being relatively easy to machine, wear resistant, and having low friction. However, there are some serious biocompatibility concerns that have caused the metal-on-metal model of hip replacements to be almost entirely abandoned since the year 2000. The main concerns being the harmful effect of metal debris produced by continuous wear. While metal-on-polyethylene implants have been historically very common due to them being well suited for older patients who have more inactive lifestyles, they also present their own unique biocompatibility concerns, including aseptic loosening and hip dislocation. Aseptic loosening is when wear debris caused by an implant creates an inflammatory response resulting in bone loss. Aseptic loosening is the cause of 24% of all hip replacement revision surgeries, making it the most common issue mandating a revision surgery for hip implants. Ceramic-on-ceramic implants were launched to be an alternative to metal-on-polyethylene hip replacements, and they did not have issues with aseptic loosening. Ceramics have many material properties which are desirable for hip replacements, such as scratch and wear resistance, hardness, and inert debris. The inert nature of the wear debris from ceramics limits concerns over biocompatibility that is present with metal implants. However, ceramic-on-ceramic implants can be very costly and can chip if not surgically inserted correctly. Like ceramic-on-ceramic hip replacements, ceramic-on-polyethylene implants have many desirable material properties, including wear resistance, scratch resistance, and smoothness. However, they do have a higher wear rate than ceramic-on-ceramic implants.
The type of surgery will impact the patient tremendously. It is typically a posterior surgery, meaning that the implant is installed from the rear of the person. This will vary as some conditions will lead to the people needing different types of surgeries, but this posterior surgery will require many cuts and a large amount of tissue to be bypassed before getting to the hip joint. It will ultimately lead to a better view of the hip for the surgeon. This surgery is less technical and will cost less and proves to be more beneficial for the average person, and that's why it is so common. The next thing to consider when discussing the hip implant is the sizing for each patient. People should discuss details with their doctors and make a decision based on the conversations they have with them. These implants are not fully customizable, but the patient does get a fair bit of choice. People have different body geometries requiring different sizing of all parts of the implant. A larger femoral head seems to improve the quality of life for one more drastically than its smaller counterpart, but wears at a faster rate and is less cost effective. The femoral stem will likely be on the longer side, as this sort of implant has the longest running data, yields more stability, decreases pain throughout the lifetime, and has a quicker recovery rate. This longer femoral stem does require a more intrusive surgery and for more of the patient's femur to be sacrificed. Sizing and the choice people make are important factors, but how much of the implant is really customizable? The implant must fit the patient, which is ensured through a series of 3D scans, computer models, and softwares that determine the size, shape, and geometry of the implant needed. This software will determine specific parameters for which the implant must be based off. Most of the pieces chosen will be of predetermined specifications and sizes, so several choices will have to be made, but rarely do people get fully customized pieces. In this case, the implant costs a fortune. The main choices a patient gets is the femoral stem length, femoral head size, the materials in the implant, the fixation method of the implant, the brand of implant they use, the surgeon installing the implant, and the surgical approach.
Future advancements in hip replacements will consist of better materials such as cross-linked plastics or ceramics, which will increase the longevity of the implant. Advancements in 3D CT scanning tech will improve the accuracy and precision of machined parts, helping design the implant to be more compatible within the body. In the near future, hip replacements will be performed using robot-assisted machines, which will greatly improve the speed and execution of surgeries as compared to a human. In the long term, tissue regeneration practices such as stem cells or biological meshes could provide hip replacements without the need for hardware installation in the body, though this process is still highly in development.
With a new hip implant, patients who were once experiencing significant pain and decreased mobility are able to experience a drastic improvement in their conditions and overall quality of life. That is why it is crucial that hip arthroplasty implants are optimally engineered for the mechanics of the human body, as well as the biocompatibility, sustainability, manufacturing, marketability, consumer compatibility, and implantation factors that we have discussed. In order to inform viewers in a quantitative and actionable manner, data has been compiled and analyzed from a variety of the sources listed here. Thank you.